This presentation is recorded on the seminar on electrochemistry. I will speak about several hard cases that we discover in the water research community, and about methods, electrochemical methods with impedance spectroscopy, excitation spectroscopy, how to handle such problems. So, this presentation is split in 3 blocks. So first I will speak about why that problem are so hard, about methodology and metrological problems here. Then second block about electrochemical approaches, excitation spectroscopy, and some accompanying phenomena of thermal or surface, for instance, character that accompany electrochemistry. So, and finally, I would like to exemplify whatever I said in 2 previous blocks with examples from our praxis. The presentation is about 40-45 minutes. So I will do several disclaimers in the presentation, and the first disclaimer is, of course, this lecture is not about basics of electrochemistry. There's a huge area has been developed over 50 last years with multiple applications for the surface research, battery development, and similar areas. So if you are not really familiar, please take some textbooks, notes, books, papers, make familiar, because this is definitely very useful tools, especially if you work with fluidics. So now the first point that I would like to discuss, of course, this hard case, metrology and methodology. First of all, what we are speaking about. So I take as an example a typical case what we have in many laboratories is one of original problems and equations. So we have here experimental system, and here we would like to explore this or another experimental factor. For instance, in our case, we take a laser light. So a classical example, that we put laser light on fluid. And we ask ourselves questions like, for instance, what are biological effects of activated in this way fluids? Can I improve my approach? So can I improve my imprinting system? Can I, for instance, so whether my system generally work or not? How to improve it? And then similar questions. And here it's important to remember. Of course, we are measuring this, and important to remember what is a measurement measuring process. So in the measurement, we always compare something unknown. So here in our case, this experimental fluid here with something known. So this is our control fluid. And we should ask the right question with the right methodology. And exactly this sentence gives us a sort of guideline how to ask your question, how to perform your measurements. For instance, it's very important that the unknown quantity and known quantity have the same dimension. So it makes completely no sense to compare kilograms with kilometers because the result is undefined. Exactly in this way, here, if we, for instance, explore some pharmaceutical effects with fluids, and here we're measuring pH of fluid, that make no sense because they have completely different dimension. We cannot answer a question from pharmaceutical area by measuring pH of fluids. That's the first point. Second point, sometimes we are clear about unknown effects here because we are exploring them, but we are not so clear about control fluid. What are our control parameters? So, for instance, again, if we compare here some energetic excitation of atomic layers, for instance, we don't know what we are measuring then here, because here we definitely measuring something different. So in this case, make sure that you do not compare unknown with another unknown. So otherwise, again, the result is undefined. You will see some spikes, for instance, some irregularities in your data, research data or measured data, and you will not able to understand them to give any meaning to this variation because we don't have a model of this. Okay, second point, please think about comparison has always a limited accuracy precision. and repeatability, I will speak about this separately, but this accuracy is precision is not the same. So this picture gives you more or less some idea how they are different. For instance, here is the case if we have high accuracy and high precision, and we could say, well, in this way we achieve a high repeatability. But if we, for instance, work with quantum phenomena or phenomena that involve to some extent quantum effects, so and then we have observer or experimentator that also influence your result. So the repeatability is no longer defined by your inaccuracy, but also defined by methodology of your experiments. So in sometimes your experiments will not have a high repeatability just because you use methodology that do not, let's say, assume a high repeatability. Just make sure that you use, let's say, a proper way to describe and to design your experiment. Another important point here, for instance, observability. Observability means that you have a model of your system and you can correlate internal states or internal variable with with data what you are measuring. So by measuring your output, you can correlate your output with your internal state of the system. So you have models. You can answer questions why and how. But if you don't have this model, so you can only monitor data. And monitoring is completely different. You just monitor normal output, normal dynamics, and you can detect anomalies. So you do anomaly detection, and by detecting anomaly, you cannot really answer a lot of questions. You just say in some cases you see one type of behavior, in another case you see something different. That is all what you can answer. To give some, let's say, examples here, just what I said in the beginning, this real question what we receive in our support. For instance, for this sort of systems, what are biological effects? So first of all, for biological answers, you need a biological test system. So this is really important. You cannot answer biological questions by considering fluidics. So you need biological system. Then even if, for instance, you have biological systems, question is what kind of biological effects. So do you consider plant physiology? Do you consider specific elements in this physiology? So you need a model, and without model, the answer is undefined. So you cannot answer questions like what are biological effects. Another point, how to improve my activation system. So again, the system is not observable in many cases, so we don't have a model. And we don't have any ideas what are internal variables and how these internal variables are related to your system. So we cannot answer this question. Same way is the system work. We don't know. For instance, here in multiple cases with laser light, you heat up your fluid. It's extremely sensitive to temperature. You put additional optical energy. And the question is this what your system doing? I mean, heat up the fluid? If yes, then of course you have this effect. But if you do, for instance, something so from infarceutical area, this heating up the fluid properly is not what you are looking for. So please be careful with sources of inaccuracy. In some cases, whatever you consider as an output and you see some responses is not your working parameter, but something would create inaccuracy of your measurement. So there's a few examples why these cases are so difficult. The most common problem, of course, we do not have a model. And we can say, well, it's a sort of small problem probably that will appear only in cases like this one. But not really. We have a number of different areas which are the same problems. For instance, I already mentioned multiple number of times infarceutical production. This is a new, extremely, let's say, fast developing area of water research in the water research community. Then we have, of course, non-chemical treatment. We have distant phenomena. We have a number of biological effects. It's, by the way, a well-known area of research here. And all of them are no longer some, small boundary problem that nobody care about. For instance, non-chemical treatment, agriculture is a main driver for non-chemical treatments, because in agriculture almost all chemical approaches with pesticides are getting more and more forbidden, and people start to look for non-chemical treatments of water, of let's say seed priming with non-chemical methods. So it's become more and more important and popular here in agriculture. Distant phenomena in the modern terminology, if we think about quantum chemistry or quantum biology, it's entanglement in macrosystems. In 2025, we have about also more than 3,000 papers published in this area. So it's a huge modern field of research. It's getting more and more in the main stream science. And same, for instance, biological phenomena as a whole area of biophysics deal with weak impact factor, with weak magnetic fields. Though there are, also at least all this area are extremely important and getting more and more importance in the science and technology. And almost in all this area we also do not see a clear test quantity. So there is mostly unknown. We don't know what are internal variables, so we don't have models. Sometimes because it's exploratory work, but sometimes because we don't know exact nature of these approaches. For instance, in the macro entanglement, we still don't know. We know that the effect takes place, that is happening, but we don't know why, what are main impacting factors, so we still don't have any models here. So in some cases this system is not observable, especially in case of non-chemical treatment, because there are many different approaches how to treat your fluids. So, and for all of them, of course, we do not have any measurement model and no structural model as well. So we can do only monitoring with anomaly detection. Same for inaccuracy on different years, so no models. So generally how to handle it. In the history of this approach, let's say, we know this, we know how to solve it. We need a sort of universal unit to compare different phenomena. Very famous example is kilogram. For instance, instead of using multiple definition what is a unit of mass, so everybody decide will choose a universal parameter and will compare different object with exactly this element. So in this way we can make conclusion, we can do a comparison between different elements, and so on and so on. And so appears the idea of this étalon of measurement unit. So here in exactly the same way, we look for a test system. So with exactly this system, we can compare different processes in all these areas, and so make conclusion, do a sort of comparison, improve our equipment and similar approach. So we need test system. I think the question of test system in that areas started from late 70s of last century. So it's about 50 years in the research. Why this is so difficult, let's say, I had to find the system so difficult, because of very contradictory requirements. And so first of all, it should be sensitive, because we do almost everything at the level of noise, in the range of noise. But from another point of view, it should be low noise, otherwise we will not see anything. So this, first of all, to some extent, extremely contradictory requirements. Another important point, the response. So we put different stimulus here, and we of course observe some response. And this stimuli response capability should be unspecific. So the system should not specifically react on, for instance, phenomena from this area with phenomena in this area, or with phenomena in this area. Otherwise, we will be not able to compare all different responses. So the system should provide unspecific response. Next point important for units, for standard units, is of course reproducibility of this test system. So this test system should be reproducible in any conditions, in any laboratory on the Earth, in let's say any place on the Earth, and should have comparable properties. If we will not able to do this, so we will be not able, of course, to compare all our results. So problem is known. We already have some proposals from optics, from aquaphotomics, from semiconductor research, from biological measurements, how to organize this test system. And of course, electrochemistry propose also some, let's say, systems or reactions as a test for such. And I will speak now about all these cases. So, electrochemistry and test reactions from electrochemical area. First of all, what is electrochemistry? So, another disclaimer, again, this is not describing the whole electrochemistry, it's this only some idea why we use electrochemistry. So, generally we can interpret electrochemical approaches in this way, so we have some macro processes of physical, chemical or biological nature, and they of course are based on molecular phenomena, physical-chemical changes. And the point is here that all these molecular phenomena can have electrical signatures. All these signatures are different. In some cases, we, for instance, have redox reaction. We can directly measure potential, electric potential. In some cases, we have ionic kinetics. So ions are carrier of charge. So we can explore different electric current flowing through ionic systems. So in this way we can explore that effects. In some cases we have only capacitive effects, for instance near electrodes area, so measuring capacitance. But in all these cases electrical signal is a very useful way for measuring because it's well measurable. Equipment is not expensive. We do not have in these electrical measurements qualitative changes like for instance in optic. If we go below 200 nanometer, everything becomes extremely expensive. In the same way, if we go over 1000 nanometer in near infrared, again everything become extremely expensive. So here all these electrical measurements have more or less some equal costs, and this cost effective, though not let's say not so expensive like any other approach. Another point, physical chemical changes have well-known models. For instance, physical kinetics, for redox reactions, we have different models for ionic Ross reactions in different, for instance, system, biological process. And the point is, if we know this model, we can demystify these complex processes. For instance, in our practice, we frequently receive questions: what are frequencies for some, let's say, ionic group or some phenomena, and we do not really understand what this mean, these frequencies. But after our discussion, it appeared that this is persons are speaking about radionic frequencies. So that you know, there's a whole area that specify what which frequency influence which biological object. So in this case, we do not speak in this term about system. We speak about known models, and if we know this basic known models, we can easily demystify process. For instance, why this change is happening, or for instance plant physiology, why for instance we have the higher fluids flow or lower fluids flow, why the different stresses appear. So we can contribute to understanding this complex process. So it means to some extent we a little bit switch or reformulate the problem, for instance with this sort of measurement, in the terminology of ionic processes. So what are known quantity? There's definitely different ionic processes, variables, kinetics or near electrode effects, redox, reactivity, impedance spectroscopy, all these different phenomena. We know models, measurements model, structural model. We know what is a source of inaccuracies, how to improve our measurements. So this more or less understanding of the system in specific language of electrochemical phenomena. Of course, and even in this model, if we, for instance, have links to, let's say, aquaphotomics, we will explore these links, or we see a links to ortho and para isomers. For instance, we have a link with nuclear magnetic resonance, so it's still, as this model is linked with all different phenomena, but as a main language we use ionic phenomena. So this is the first, let's say, understanding how to use it. Second point, generally, how do we measure everything? Here again, disclaimer, it's only a general structure, so of course we have much more details on each of this level, but in some common level of understanding, you can think about electrochemical measurements as a sort of excitation spectroscopy. So you stimulate your system, your ionic system, with a current on specific frequency. Waveform typically is a harmonic sinusoidal signal, but in the same way people use, and we also use step function, also different waveforms. And here you can scale up your frequency, so step by step increase your frequency, and so you produce a spectral analysis. So your response will be also split over different frequencies. And here, as a response, you receive quite complex signal, and this signal include ionic responses and include different subphenomena. So typically what we see, of course, impedance, and we can calculate conductivity at a given frequency. We have correlation, phase, Nyquist plots, electrochemical noise, some thermodynamic data, frequency, time frequency pattern. I mean, we really have a lot of different parameters. So typically, for instance, with our system, you receive about 35 different data channels, and so all of this data channel has useful information. So you can decode it, you can map on different processes, and so you can use it. There is one way of doing impedance spectroscopy. Another way, if you just instead of giving harmonic sinusoidal signal, you put chaotic signal, noise, and then as the output, the system produces a sort of Fourier spectra. But there is specific spectra, of course, related to ionic phenomena. Here we have artifacts related to sampling frequency in DAC or in ADC, different clocks, so they will be, of course, visible here. But some resonances are definitely related to ionic groups, ionic processes, and those can be identified here. So there is a reason of fast impedance spectroscopy, and of course it's very fast because you don't need to scan different frequencies. So just in one step you receive a frequency response. So it's let's say some common understanding of impedance spectroscopy. Of course, we have here additional element with excitation. So we produce optical or magnetic or electric field excitation. So this is always different. To have a test response of your system to some specific stimuli. In next slide, I will show you excitation with magnetic field, but here just to say, though, we frequently combine both electrochemical impedance spectroscopy with additional excitation spectroscopy. So it's a combination approach. So finally, if you have all this data, you start with application analysis. This of course depends on your research area. You can do, for instance, like here, make equivalent diagrams, and each element will define some specific ionic process. We use the same system but with different electrodes for analyzing biological objects, plants, with plant physiology, with different models here. You can apply this with, again, different electrodes in microorganism to have some information about, for instance, fermentation stages, metabolic process, aerobic, anaerobic fermentation, and similar things. And of course, all fluidics you can explore starting from distilled fluid with test reaction up to some suspensia with different components. So it's well applicable in, you see, a large number of different areas. So now back to the point of test reaction. If you perform impedance spectroscopy, and start with, for instance, distilled fluid, distilled water, you see a sort of degradation. So it's a slow process. You start with, for instance, high impedance. It goes low up to the level of, it depends. of course, but up to the level of 60, 50, 40 kilo ohm, and then become more or less flat. What is happening in this case? We observe here electrochemical degradation. And this electrochemical degradation is described by several approaches. For instance, self-ionization. It's quite slow dissolved gases, so most of them CO2. And exactly these dissolved gases attracted our attention because this this approach can be used as this test reaction. So just to explain what I mean, here I took this presentation from Roger Williams University, because the whole topic is important. It is about carbon dioxide in oceans and climatic changes. But this characterize different stage of CO2 dissolving. So just to give you the idea, first we have dissolved gases. In the atmosphere, they become dissolved in water, and then create two important stages. So first with carbonic acids, and then in ionic form bicarbonate and carbonate. So important here consideration is, first of all these elements, they are in equilibrium stage or go to equilibrium stage. And exactly here, for instance, if the system here achieve this flat phase, they achieve equilibrium stage. First. Second, all these reactions are reversible. So it's depend on concentration of these products, and if concentration here is let's say higher, the system go in the reverse direction and will produce carbonates, so bicarbonates from carbonates, and carbonic acids from bicarbonates. So the system is reversible. It's a most important this transition, because here we exactly work with impedance spectroscopy. We sense transition between ionic and non-ionic stage. And so here the point is this process is extremely sensitive to environmental condition. Temperature, for instance, here in the ocean research, once again, we see a very different concentration of CO2 along, for instance, measured islands, with CO2 level, with different, for instance, most of CO2 is stored in the form of bicarbonates, so we have different level. So this very sensitive to this environment conditions. The important point is the rate of electrochemical reactions also depend on conditions. And so why the rate of reaction is important? Because it's easy to measure. So here we see with this, for instance, inclination of this curves, we see speed of this electrochemical reactions or electrochemical reactivity. So this reaction demonstrate variable electrochemical reactivity, and this variable electrochemical reactivity depends on different external stimuli, intensity of, for instance, influences, energetic excitation, and all different parameters. And so the idea is very simple. We will take changing of electrochemical reactivity as our test reaction. Okay. Now, another advantage of this CO2 dissolving process, also to be honest, this of course the CO2 dissolving is a little bit more complex because it's not only involve purely chemistry, it involves physical chemistry. And so we have several boundary cases, the solvability, and several other topics. But in our representation, just important to understand if we use as a test reaction. So for test reaction, it's well reproducible. If we have, for instance, CO2 atmosphere between 400 ppm up to 1000 ppm, it's not a problem at all. So we will see a little bit different inclination, basic inclination. We can adapt the approach. So this is very stable. So we can use either this fast degradation stage up to reaching equilibrium, or even equilibrium stage, because even in the equilibrium we still see the change between ionic and non-ionic form. So the reaction, we can work with this reaction in the duration of months without changing fluid, without changing the system. So it's quite stable condition, and so it's absolutely absolute advantage for using this as a test reaction. Okay, now like I said before, a little bit about excitation and excitation spectroscopy with magnetic field. So how we tested it? We use once again fluids. We put, open it, put access to CO2 here, and as additional excitation, we use magnetic field. We test it in different ways with optical, magnetic, electrical field excitation. Here, magnetic field, because at least in this paper we go in the way of parent ortho isomers of water, so we would like to test it, of course. And here is the excitation by magnetic field. This is very weak, between 200-300 microtesla up to, I think, 900 microtesla. So we are in the microtesla level. And so what we saw in this setup, first of all, if we do not have CO2 dissolving, control and experiment are very similar. So there are no essential changes, exactly as it is expected. As soon as we put a test reaction, we see different stages between ionic and non-ionic product, and exactly this point they are electrochemical markers. So based on this point, we already see a lot of short-term phenomena. So with these markers, we can characterize short-term behavior. Another interesting advantage, we do not only see short-term phenomena, we see a long-term phenomena. So exactly because if we excite fluids is able to store energy. And the question is in which way it store energy. It's still open because there is definitely non-chemical energy. We can store energy, for instance, in different electronics level in the atoms. We can store energy in form of different isomers. And exactly what we see even after hours, sometimes after days, we still see oscillation, electrochemical oscillation in the fluid. So here, if we just think again about different ionic, non-ionic form, we see oscillation between two different forms. It means that energy is still present in the system and we can explore it. So this is definitely advantage. Another point, like I said, this reaction is sensitive to excitation energy, to excitation level. We tested it with different current. So you can think here is about 300 microtesla, about 900 or similar, but low level magnetic field. And these electrochemical markers again, and we see that the level of inclination between electrochemical markers is always different. The larger inclination, the more is energetic influence. So we are able to measure different levels of excitation. And this not once again is not only magnetic field excitation, the same way is optical or any experimental test what we are using or you are using in different system. So we can measure with this test reaction. We tested not only CO2 dissolving, also hydrogen peroxide dissolving on all these reactions that appear after even if you put a small quantity of hydrogen peroxide, it's also well suitable. The question is, of course, how it's appear or how it's possible. And this is my standard slide in all presentations. We still think that the main mechanism, at least that work in the level of physical chemistry, because here we have, of course, different mechanism. This was one of them. This related to isomers, nuclear isomers. And the idea is here that we have a different rotation of hydrogen, of protons. A few things what is important to memorize from this slide. First of all, we have chemical side and we have quantum side. So in this way, this the same water molecule, just to remember, it's the same water molecule, but with different rotations of protons. So can represent a sort of quantum sensor. So we are able to sense quantum from quantum, all these phenomena from quantum side by measuring chemical side, chemical and physical side, and vice versa. If we change chemical and physical sides, we can influence quantum side. So that's absolutely a universal bridge between chemical and quantum side. So that's the first point. Second point. this is the same molecule, water molecule, but they have different chemical properties. And the one also important is reactivity. They have different reactivities. The difference between, let's say, 20, 25, 30% depends. And exactly why we see different inclination and different intensity of our CO2 reaction, because it has different reactivities from this isomer side. Next thing, important, this has not only different chemical reactivity, but this also influence physical properties like viscosity, surface tension, thermal capacity, and similar effects. So if we will measure all these phenomena, we will also discover changes. And the last point, the energy between different isomers is not so huge. Some colleagues make estimation of this energy is about 10 of power minus 26 electron volt. It's very low value. And of course, probably, I mean, this low energy interactions or energy less interaction exactly appear because of this low energy of spin conversion process. So this little bit about this mechanism. Finally, if we, let's say, go from to viscosity surface tension, this is very easy to test and to see. Even in the microscope, this is exactly our electrodes. If we see, if we excite fluids and observe in the microscope the surfaces, they start to oscillate a little bit. It's well visible sometimes. And for instance, the short-term oscillation of experimental fluid are exactly defined by this changing of surface tension. We tested it in the way of putting capillary tubes in the fluid, and it depends on the which depth you put your tube. But if you put, for instance, here in the surface level, the difference in the surface tension between excited non-excited fluid is about 10 to 15%. So it's quite essential. Then for thermal capacity, we measure thermal capacity. The system has different thermal capacities. So this excitation change thermal capacity, and sometimes we even observe the oscillation of temperature inside of fluids in exactly the same way, like here. And once again, it seems impossible, yes, from normal thermodynamics. But if you think in terms that this reversible reaction, one of them is endothermal, another is exothermal. And we change thermal capacity of the system, we could have thermal oscillation just because of changing thermal capacity. So this topic is not about electrochemistry, but it is accompanying phenomenon that can be measured, and by measuring these effects, you will receive more or less similar result as measuring with electrochemistry. So it is, we published this. You can find more details. Now to conclude. If we use reaction of CO2 dissolving oxygen or hydrogen peroxide, so all of them are excellent candidate for test reaction, especially CO2, because it's easy. You don't need to put anything additional, just open the container and take CO2 from atmosphere. So it's absolutely, easy to reproduce reaction. So you receive additional phenomena that are measurable: viscosity, surface tension, and thermal capacity. And in this way, you also receive a capability to test some quantum effects. Probably in examples, what I will show you, we will exactly observe this bridge. So system become observable. You know exactly what is happening inside. You can formulate. You can describe your phenomena in terms of this model. You know what is happening on the level of measurements, on the level of phenomena itself. You know what how to improve. What is the influence of, let's say, chemical purity, temperature, and the most important is very reproducible. And so. Proposal, or let's say idea, what we do in last years is just to use this reaction to characterize difficult cases that are in the boundary of measurability. So now I would like to exemplify whatever I said before, to exemplify with examples. The first example, of course, this very well-known example with active fluids. If you this first time we discovered this with Urs Zurbeck, he is already unfortunately passed away, but the first time we measured this example. If you take for instance this fluid, you put it outside of your container, thermal container, to isolate all these thermal effects. Inside of container you have test reaction of distilled water with CO2. You will see something like this, and then seems to be impossible, because how passive fluid can change your electrochemical reaction, but it's happening. Later on, let's say this first time we discovered it, it's about 2015. We conducted really large number of experiments to understand this phenomena. Finally, we formulated in the way of synchronization of molecular electrochemical oscillators that is involve different entanglement phenomena and molecular scales. I would, if anybody is interested, please check this paper. But this is definitely an interesting example what you can sense with these test reactions. Another interesting case, this more related to biological measurements. This first time we tested this in 2017 in the conference, water conference, from Jerry Polak in the Sofia in Bulgaria. This very famous person, Ricci, she healer, and we asked whether she can modify properties of fluid, and she put hand here water container, and we ask first to increase reactivity, so to produce more ionic products. It will be visible by changing of colors, and the second time to produce a reversible process, to reverse in sense to decrease amount of ions, so to decrease colors. And she done this just in terms of 10 minutes. You see, so we see well observable effects. And this is produced by intention, so it is intentionally produced reversible reaction. So it seems human person is able to do this change intensity as electrochemical reactivity in two opposite directions. So it's also using of this test reactions very sensitive in this way. Another way, if you speak about biological phenomena, there is some theory that all these biological organisms have a sort of field. Biological field is not a secret, of course. We have, of course, terahertz emission, electromagnetic emission, magnetic field, electrostatic discharge. All this, as any object on the Earth has this. But it seems there is something additional, and there was a long time discussion what it is, how to measure it. So we also conducted a number of experiments. In this time, we used pH. The same electrochemistry, but with different ionic kinetics. This highly thermostabilized system. Here we put a sort of metallic shield to avoid all this discussion on electromagnetic processes. And what we saw, if we insert or remove this fresh cut leaf, we see a change of electrochemical dynamics. So again, from the point of normal chemistry, this is impossible, or physics is completely impossible. But if we now think in terms of new quantum chemistry or quantum biology, this example how it's work on this level. So we publish it in 22, and once again, here we use this test reaction. It's extremely sensitive even to this sort of approaches. We like, of course, exploring distant effects. Started more than, I think, 15 years ago with such tests. There's from two examples from good old times. Long-term interaction, 2,000 kilometers, about 8,000 kilometers. As activator, we used in those times these optical generators. But anyway, in all these cases, you see a change of electrochemical reactivity in the system, and once again there's a large distance. Even in this case, we assume there's a sort of proton tunneling, so the fluid responds by another quantum phenomena. So this explains this change. We from time to time we observe this as well. So, but again, this test reaction is extremely sensitive to distant phenomena, and the assumption is why, because exactly of this quantum chemical bridge. So any changes on quantum side produce chemical changes as a change of reactivity that we are measuring here. So we just to underline another disclaimer, we still don't know why it's happening and how this macro entanglement works. We test different approaches for this, but still, I mean, you can test it, collect statistic, test different systems just with this approach. So this again is a modified from 2024 with Kishinev, with Sergei Maslobrod. He is author of this experiment. So the idea is in Kishinev, he used 3D color sprouts, a switch on, switch off light. And in Stuttgart, we have a digital representation of this object. So distance, once again, 1,500 kilometers. And we use impedance spectroscopy with digital representation to test changes in the original object. So, and if we recorded everything, and then after this analyze, and if we saw this, for instance, rapid changes in electrochemical dynamics, they exactly correspond with the times where Sergei switch on or off light. This, again, crazy idea. Here is a point, we still, like I said, don't know why it's happening, how to entangle different systems, but it's just one example how you can detect different distant phenomena by using test reactions or changing of electrochemical reactivity of test reactions. Another idea, we also like very much this approach with mind, because consciousness, so we as a biological object, we of course capable of inducing this distant phenomena, interact with our consciousness, with physical world, and once again this can be measured. So we approach this technology, mind technology, so with two feedback, as a local feedback to monitor your physiological state with EEG, and you use electrochemical sensors, distant sensors to give you information as a feedback loop about distant phenomena. Then so this system is already a long time in the market, so many groups use this. Web pages, individuals, so researchers. So there's currently really a large statistic accumulated. We publish, people also publish this. This fine, and this one example from this year's from 25 distances 500 kilometers from Joule, and the test session, so 2 persons participated. Here is a test, so session is about 10 minutes, and then exactly you see after the session reaction, the change of electrochemical reactivity. So here the system achieve equilibrium stage, and it switch to backward reactions in opposite way and change a sort of relaxation. Those are the typical examples how it works, for instance, with electrochemistry. So here is the last slide, same mind, and we produce a sort of distant influences like I described it in the previous slide, and compare with Reiki. And you know, in the case of Reiki, you interact with something, let's say some network or some more highly developed object, so different interpretation, but nevertheless we see clear difference between both. And so the idea is probably, if we speak in terms of para-ortho isomers with quantum object, and we have a huge number of quantum objects everywhere, even here in the room, all this, for instance, in vapor, we have different isomers. They interact with each other, they create network. And the question is, so definitely this network is capable for information processing. So in AI research, there's already some investigation how we can use this computation also in this environmental networks. So the question is, why we cannot assume that this sort of network exists and we can interact with this network. So this, let's say, approach what we're exploring now. But it seems that if we use this network, we can achieve more higher score, at least in the mind technology. And this is, of course, of large interest. And the last example, for instance, again, consciousness. The system, mind system, is sensitive to meditation, to consciousness. Here is example with Buddhistic monks. Here is the system one times here, one times over the wall to avoid this thermal phenomena. So here all person enter in the room. Here is a meditation, and you see this change of electrochemical reactivity exactly during the meditation. So there is not, let's say, this does not react on entering person in the room, not when person left the room, but only on the meditation time. So it is more or less interaction with human consciousness. Just once again, the test reactions, those CO2 dissolving, is sensitive to also this sort of interactions. Okay, short conclusion. What I can say, first of all, of course, electrochemistry can be used as an étalon, as we propose at least étalon here for these hard cases. So as a test reaction, please we test the 3 test reactions. Most useful probably CO2 because of easy reproducibility in any condition everywhere on the earth. So we will have same reactions. So of course, discussion is how all other environmental conditions influence it, because so if this reaction is sensitive even to mental phenomena or biological effects, of course all this phenomena in your environment will influence this test reaction. But at least this will be a sort of experimental factor that you can explore. The test reaction itself is well reproducible. If we use this, we of course introduce observability, known variables and known models as a huge advantage. We have common language to describe phenomena, to compare this phenomena. This is high reproducibility. So like I said, for test reactions, and most important is academic level of research. So if you formulate your result in terms of ionic groups, ionic products, para-ortho isomers, or thermodynamic effects, or viscosity, is completely different level of representation if you speak about radionic frequencies. So in these terms, like I said, in the progress of quantum biology, quantum chemistry, also this become more or less academic level of research. It's easy to some extent, of course, to publish, at least in some preprints or even journals or conferences. So, and it's used, let's say, language that is understandable in the community. So finally, what we can say, at least AIS and MIND is already about 7 years on the market. Of course, huge number of experiments. In MIND technology, we started already to differentiate between specific cases. This could be, for instance, labeled as MIND mother and MIND mother mind. So experiment. So it's a little bit different. And we think about now existence of external quantum networks, for instance, spin isomer network or any other. I mean, there is a large number of molecules that have isomers, spin isomers. Though existence is highly possible. So, and even the groups in the world, they start to think in these terms. So I think if we use these reactions, this test system, we can at least start to use same language like all of these groups. Okay, thank you very much for your attention. If you have any questions or suggestions or let's say some discussion, please contact us or contact me even. So personally, I think we can establish some discussions here. Okay, thank you, and see you next time.